public health seminar. And I'm very pleased to present our speaker for today, who is Dr. Christy Costanian. She's going to talk about overview and use of longitudinal data in epidemiologic research. Dr. Costanian is a chronic disease epidemiologist and a research faculty at the Lebanese American University in Beirut. Her research centers on chronic disease factors and outcomes, global health, and women's health. Some projects that she is currently involved examine the intersection between reproductive health, cardiovascular health, and brain health. She's also interested in longitudinal data analysis and systematic review. Dr. Costanian completed her PhD in epidemiology at York University, Toronto in 2018, and then she pursued a postdoctoral training at the University of Ottawa. So it's a pleasure to host this seminar today. Just a couple of things. I would ask everyone to keep themselves muted, okay? And keep your questions, please write down your questions and ask them at the end. We're going to ask you to use the raise hand option to be able to manage the questions and the order of questions. And thank you everyone for being with us today. Today we're going to have 1 hour seminar. We will keep it exactly 1 hour because of the power related issues in Lebanon. Dr. Costanian, the floor is yours. Thank you for being us with today.
Thank you. Thank you so much for this introduction. I'm very happy to be part of this seminar, and I'm very happy to meet with you and engage with you all. So today we will be talking about using longitudinal data for epidemiologic research, a quick overview on some of its methods and its features, as well as the issues that one might face using longitudinal data and secondary longitudinal data. So a bit of a background about myself, and I don't know why okay, sorry, bit of a glitch here. So as Vardi mentioned, I'm a chronic disease epidemiologist, and my research interests lie in women's health, chronic diseases, health behavior, and survival analysis and longitudinal analysis methods. And here are my credentials. And I'm currently a research faculty at the School of Medicine at the Lebanese American University. So today, our objectives for this talk will be to examine longitudinal cohort design topics and issues, discuss selected statistical analysis topics, and explore some examples of pre-existing longitudinal data sets that can be used and that are publicly available. So what is longitudinal or cohort study? So as you may know, it involves the follow-up of a group that, let's say, has a disease and a group that doesn't have a disease over time, and to observe whether an outcome of interest occurs. And it's unique in that the passage of time is incorporated in the study. Now, the measures that are observed over time can be made either repeatedly throughout the study or only at the beginning or at the end of the study. And the focus of the study may be specific to study a certain hypothesis, or it might be just descriptive to gather data on various measures and to generate hypotheses. And it can be broad testing multiple hypotheses, and its objectives might change over time. But one thing that's certain in a cohort study is its dynamic nature, whereby many risk factors can be explored in relation to an outcome, and people can come in and out of a cohort depending whether it's an open or a closed cohort study. So just to go into more details of the features of a cohort study, it requires primary data collection. It's usually expensive to set up and to design. It's generally available at a minimal cost. We'll discuss this in further details later on. And it's based on recruitment that may or may not involve incentives and may or may not involve healthy volunteers. It's scheduled and continues as long as funding is available, and it's based on established protocols. And any outcomes and severities are specified beforehand, usually by the investigators, but it is amenable to change. These outcomes and measures can be modified at any point in the study. And its strength is that it's usually done on a representative sample. And although it does suffer from attrition, but on the whole, usually follow up for a long period and a robust recruitment prevents attrition. So how is a cohort study usually assembled? Either by geographical region, for example, the Framingham Heart Study, which is a very famous study on the risk factors for coronary heart disease. So Framingham is a small cooperative community that lent itself to this study, and it's now on its third generation of participants. Family members of the original cohort are now enrolled, and the study uses rigorous and standardized protocols for data collection, and it lended itself to many methodologic advancements in longitudinal data. And its importance is that it predicted risk factors for heart disease. And that was back in 1967 when it first started. There are studies that have been assembled based on occupational groups, such as the Nurses' Health Study, the British Doctors' Health Study, Gold Miner Study on tuberculosis in South Africa. I'd like to note the British Doctors' Health Study, which is also a very famous cohort study, which was done between 1951 to 2001 by British epidemiologists, the famous Richard Doll and Austin Bradford Hill, along with Richard Piro. And their objective was to study association between smoking and lung cancer. So this study of British doctors enrolled more than 34,000 British male doctors and recorded their smoking habits, their conditions, and the development of lung cancer. And later on, this study recruited women physicians. The cohort can be assembled by a disease or a condition, such as the multi-center AIDS cohort, by risk groups, vulnerable populations, such as the San Francisco Men's Health Study, or by a unique exposure event, such as the Japanese atomic bomb survivors cohort. Over here is the site of the Framingham Heart Study that's also been ongoing with the third generation participants, so the grandchildren of the original cohort. And here is news clip on Sir Richard Doll's, the late Sir Richard Doll's obituary and his seminal work in the British doctor study. So what are the advantages of longitudinal methods? There are many. The first one being more flexibility in research design, since not everyone is following the same rigid schedule, and indications for following up a person, they're not fixed, and you don't have to follow them up for every wave. Second, you can find temporal patterns. The effect of time is clear in terms of the outcome. Does it increase, decrease, or remain stable? Are there shifts? Are there changes? Is there a linear pattern? Also, an important advantage is the possibility of including time-varying predictors or time-varying covariates. So variables whose values vary across time, such as weight, blood pressure, even smoking, and these are really key in understanding longitudinal associations. Also, it can incorporate interactions with time. So whether an effect decreases, increases, or are pronounced. So what are the research questions, however, that lend themselves to longitudinal methods? So you'll notice that the main theme in longitudinal data is time. So questions can be either about a systemic change over time. So for example, change in BMI, change in blood pressure, change in cognitive function, or questions about whether and when events occur. And here are two examples of each situation that can be analyzed using longitudinal methods. For example, for questions about systemic change over time, infant neural function can be studied. And we want to see whether infants exposed to cocaine had lower rates of change in neurodevelopment. Of course, infants exposed to cocaine in the womb. And we want to see how does an infant's neurofunction change over time. That's our main objective. So, which is within person, and what is each child's rate of development given their exposure, and how do these rates vary? Usually, questions about change over time are modeled using multi-level or mixed models or latent class models, which we'll discuss further in a bit. Now, questions about whether and when events can occur, these are more common. You see such questions more using cohort studies, and they are usually for disease outcomes. So when does a disease occur, whether does it occur, and what are the factors that affect its occurrence over time. So for example, marriage duration, we wanted to see whether couples in which the wife was employed tended to divorce. So the event was divorce in this case. And usually discrete and continuous time survival analysis is used to assess such questions. Now, what are some types of outcomes in a cohort study? They can be discrete, such as single events, for example, mortality and occurrence of a disease, incidence of a disease or a condition, cumulative incidence, or they can be multiple occurrences of disease outcome, or transition between states of diseases, or between functional status. And they can be a level of a marker for disease or state of health. For example, an outcome that can be assessed is, for example, albuminuria as an outcome of kidney function over time, or the rate of change of that biomarker, or the patterns of growth, and we can track these markers across time. So what are some methodologic and analytic advances of cohort studies? What have they enabled us to do? So again, they are a great sampling method to address the relationship between an exposure and an outcome, especially when an outcome is infrequent and needs a lot of time to develop. Also, cohort studies gave rise to the use of nested case control designs, whereby nested case control studies encompasses cases with the disease, and it compares the exposure history of the cases within a cohort to controls also within that cohort that were sampled from the same time at which the cases developed their condition. So this is a huge step forward for longitudinal methods. Whereas prior to the 1970s, which was usually like the era where cohort studies boomed, binary variables, yes, no, were the principal outcomes. However, cohort studies allowed methods, statistical analysis methods, to be extended to incorporate time, and new methods to be developed so that they explicitly incorporate time, for example, Cox regression. So Cox is the one who is responsible for sharing his now renowned proportional hazards or Cox regression statistical method for analyzing time to event data. So more analytic advances in cohort studies, they include, again, looking at markers of disease progression repeatedly, and extending GLM, so generalized linear models, to incorporate time. So GLM are incorporate linear, logistic, and Poisson, as well as survival analysis. And now they can handle time-varying covariates, and they can cope with more complicated covariance structures, such as correlated data. And cohort studies allowed us to use mixed and hierarchical models. And again, all of these models can handle time-dependent variables. So let's talk a bit now about the statistical models or techniques to analyze longitudinal data. The most common and prominent is time-to-event models or survival analysis, which we will delve into more details in a bit. Another also commonly used technique is mixed effects or hierarchical model or multi-level model. Another also becoming more prominent technique is marginal model or GE, generalized estimating equations. And another technique is latent trajectory or latent growth curve models. So just a bit of an idea about mixed effects versus marginal versus latent models. So mixed modeling, otherwise known as hierarchical or multi-level, takes into effect several layers or levels of subjects. So let's say you want to look at the factors that are attributed to school children's academic success. So there are the level of the students, then the second level of the teachers and classrooms, then the third level of the school. So by using mixed modeling, it takes into account these several levels. And so the data are in the form of one row per subject at each time point. And it can handle unbalanced data, and it allows us to adjust for confounders at multiple time points instead of only adjusting for baseline values. Now, mixed models can be either fixed effects or they can be random effects. Fixed effects model being that the dependent variable and the changes in the dependent variable that is attributed to another independent variable, another predictor, are fixed, whereas random effects allows this change to be variable for each person and to vary for each variable. So this is for mixed models in brief. Marginal models, or GE, its primary focus is the mean model, whereby every 1 unit increase in a covariate, the GE tells us its average response. So by how much its average response would change. And it traditionally accommodates one level of clustering. So it takes the correlation between within subject data, but it uses all available data per subject. Latent trajectory models, on the other hand, or latent growth curve models, classifies subjects into groups, and it was developed to group subjects according to selected characteristics. So, and those characteristics are unobserved, i.e. latent. That's why it's called latent trajectory model. So usually the approach is to estimate a single cluster where only a single group is presumed, and then more groups and clusters are added that estimate the parameters by the software, and then a final model is chosen based on model fit. So those are like technicalities in brief, so that you have an idea of the different techniques. But again, I just want to mention that all of these models are not used to model only growth or only increases, but they can model decreases and changes that, I mean, they're not consistent. So it's not only increases or decreases over time. Now, let's delve more into survival analysis, which is pretty common for analyzing longitudinal data. So survival analysis analyzes data based on the occurrence of events that may include death, injury, onset of an illness, recovery from an illness, or continuous variable based on a certain clinical threshold. And it's usually takes into account time until an event, and whereby time is survival time. So it gives the time that an individual has survived up to this outcome or event occurred. And it can accommodate data either from a randomized control trial or a cohort. And again, we said that the event can be different outcomes, such as death, disease, relapse from a disease, recovery. Usually, when the event occurs, it's denoted as a failure, but sometimes failure is a positive event. And we'll see an example of that in a bit. So again, time to event is a time from the entry to a study until the subject develops a particular outcome. This is how survival analysis looks takes into account time. Another important concept in survival analysis is censored or censoring. So censored means a person is not observed, either by not experiencing the event before the study ends, or a person is lost to follow up during the study period, or a person withdraws. So if any one of these scenarios happen, this person is considered as censored. However, if they don't develop anything, then they're considered as alive or disease-free for the time that they were enrolled in the study until the very end of follow-up. So, survival analysis is unique in that it involves events, and it involves a progression on a dimension, which is usually time, until the event happens. It takes into account time to event, but this time to event may vary among subjects, and the event might not happen among subjects, but survival analysis also takes that into account by censoring. Examples of questions or events and outcomes that lend themselves to survival analysis. For example, leukemia patients, time in remission per week. So the event is going out of remission, while the outcome is time in weeks until a person goes out of remission. So you'll notice for survival analysis, there always has to be an event and an outcome which incorporates time. Another example is developing heart disease as the event, while the outcome is time in years until the person develops heart disease. Or the event is death, very common event, while the outcome is time in years or time in months or time in days, depending on the condition that we're studying until death occurs. So here is an example of a survival curve or a Kaplan-Meier curve. And this example, we want to estimate the age at natural menopause among women. In a survival curve, the starting point is always 100%. So 100% survival, and the survival curves will start at 100% and shows the percentage of participants who are still surviving at successive times across the study. So, and as long as they have information. So for example, here, our event is natural menopause. So for every person who developed natural menopause, you'll see this drop in the curve until all of study participants have either reached menopause or the study stopped following them up. So you'll notice here that the median age at menopause is 51, and the age range is between 40 to 62. And I just have to mention that Kaplan-Meier is a non-parametric method, and it can also be applied to cross-sectional data if the time is in age. So time doesn't always have to be in days or months or years. So now we come to Cox regression, which is also known as proportional hazards regression. And this is a multivariate regression technique where time to event is the dependent variable. So if you want to think about it, if you want to compare Cox regression to logistic regression, a Kaplan-Meier would be more like a chi-square test, whereas Cox regression would be more like a logistic regression, but time is incorporated and censoring is incorporated. And the estimates in a Cox regression are hazard ratios instead of odds ratios. And a hazard ratio is the ratio of rates or hazard rates. And it is different than an odds ratio in that it's a rate, therefore it incorporates time, whereas an odds ratio is a ratio of proportions. And the hazard ratio, it estimates relative rather than absolute risk. So Cox models the effects of covariates on the hazard rate. So the time that it takes for the person to develop the outcome or the hazard, which is the risk of developing that outcome across time. And why is it called also proportional hazards regression is because of the proportional hazards assumption that underlies this analysis, whereby the hazard of any individual is fixed, and it's based on a fixed proportion of the hazard for any other individual. Okay, so here's an example of a hazard ratio from a study that looked at the association between gestational diabetes and incident maternal chronic kidney disease using data from the coronary artery risk development in young adults, the Cardin study, which is also a robust longitudinal US-based study. So if you look at table 3, where hazard ratios and their 95% confidence intervals are being presented for women with gestational diabetes, you'll notice that among Black women, the hazard ratio for CKD was 1.96 times greater for those women with gestational diabetes versus Paris women without gestational diabetes. Whereas among white women, the hazard was 0.65, and also it was non-significant. So as you can see, this table shows us the hazard ratio for gestational, for CKD by gestational diabetes status among Black versus white women. So it also shows us the interaction of race. Now we come to time-dependent covariates, which is a crucial issue or topic in all types of longitudinal modeling. Time-dependent covariates are covariates that change over time for an individual, as we mentioned. So at each event time, the model compares the current covariate values to the current values of all others who were at risk at that time. So if you want to think about it, it's like a lottery. So each event time, there's a drawing to decide which study participant wins the lottery and how likely they are to win. And the model tries to assign a risk score to each subject that best predicts the outcome for each drawing based on the risk set. So which subjects are present for each event, and the covariate values for each subject just prior to the event time. So the model compares the current covariate values for the individual who had the event to the current values of all others who were at risk of the event at that time. So let's take an example of time-varying covariates. Let's say you're evaluating the effect of weight on diabetes risk, and so subjects may gain and lose large amounts of weight. So baseline weight is not a great predictor. It's not enough to include baseline weight in the model alone. Also smoking, the effects of smoking on the risk of pancreatic cancer may change. Also oral contraceptive use and fracture risk. Many women stop taking oral contraceptives and then restart, or they just stop. So again, OC status at baseline doesn't give you the full picture of the risk of fracture. So by using Cox regression, time-dependent covariates can be incorporated. So other study design issues in cohort studies that are usually encountered. Study duration, follow-up time, it's usually very long, and cohort studies are prone to attrition. The frequency of measurements, they're usually repeated measures. So depending on each follow-up interval, measures can be repeated every 2 to 5 years. And this requires stringent protocols to be followed, and to make sure that if it's a multi-center study, that all sites are consistently performing the same measurements. Selection bias is common in cohort studies, especially if it's an occupational cohort, or there's a differential dropout among the exposed versus unexposed. For example, AIDS, the study, a cohort study looking at HIV progression to AIDS. Also, there's confounding bias. You can't account for all of the possible confounders. You can't measure them all in a study and consistently across each exam period or each follow-up period. And also, we've talked about time-varying covariates, and usually there's information bias that goes into time-varying covariates, especially if these covariates are based on self-reports. So for example, family history is a variable that is really prone to information bias because it's affected by so many other factors such as recall bias, cognitive ability, and other bias-induced factors. So that's also one of the issues to look out for in cohort studies. Now, let's talk about some of the available longitudinal data that can be used for analysis. Now, data that's primary is collected firsthand and it's generated for research purposes. such as national disease registries, whereas secondary data is data that's collected more passively and not really for a specific purpose, research question. It can be billing data, health administrative data, encountered data, or a pre-existing study. But secondary data usually contains enough to have a meaningful population-based conclusion and look at really interesting questions. So what are some of the sources of secondary data? And I'm focusing more on the US since those are the most commonly known data and that can be accessible. So the National Longitudinal Surveys of Youth is one source. There are also longitudinal studies for early childhood, National Longitudinal Study of Adolescent to Adult Health. There's also the Wisconsin Longitudinal Study. And these data can be either publicly accessed or accessed through the main PIs of the initial studies. The UK also houses some really good longitudinal data, such as the Millennium Cohort Study and the Child Development Study. Now, you'll notice that a lot of the pre-existing data for longitudinal studies are based on diseases and conditions, mostly chronic diseases such as heart disease, diabetes, and cancer. And the impetus for creating such data is because of the multifactorial nature of these diseases that include different factors such as genes, behavior, lifestyle, and to study the interaction of these factors with these conditions is really worthwhile. And chronic diseases are on the increase. So we want to understand how all of these factors play together to increase or decrease risk in order to come up with better prevention strategies or better management strategy. So this era generated a lot of longitudinal disease studies that are landmark studies that are ongoing, multi-center and large cohorts that have really robust and rich data and that have follow-up ongoing until now. They're mostly, they've been initiated by the NIH in establishing cohort studies on cardiovascular disease, such as the ARIC, Atherosclerosis Risk in Community Study, Cardiovascular Health Study, the famous Nurses Health Study, MISA, the Multi-Ethnic Study on Atherosclerosis, and also the Women's Health Initiative, WHI, and there are many others such as the Jackson Heart Study and the Baltimore Longitudinal Study on Aging, but those are the most common cohort studies that are also somewhat publicly available and that have been led by the NIH, and they're still ongoing. So an example is Nurses Health Study, whose initial goal was to evaluate OC risk. And it's now also like on the third generation. Initially, the questionnaires were periodically mailed out to thousands of nurses, but now the questionnaires are now based online, where participants have a login ID and password to complete the survey. ARIC is another rich longitudinal study that was designed to investigate the causes of atherosclerosis and its outcomes, and risk factors by race, gender, location. And it was mostly an older cohort at baseline that was sampled from 4 US communities and had subsequent evaluations. So spanning from 1990 to 2013. Now, the coronary artery risk development study is also a study that was designed to look at cardiovascular disease risk factors, but now the initial cohort was relatively young. They were aged between 18 to 30 years at baseline, which was in 1985, 1986. And it included both Black and white adults across 4 centers. And these adults were followed up across time, and it's now in its year 30 of data collection, with year 30 data being available for public use soon. Now, there's another resource that is also a great platform to examine aging, and also by means of longitudinal data. It's called the Canadian Longitudinal Study on Aging, and I've used this study many times for my research, and it's a really great source to understand the different factors that go into aging. And it has many disciplines. It caters to many different researchers in biology, genetics, medicine, epidemiology, population health. It's a 20-year study across 11 sites in Canada, with the data collection happening every 3 years. And it includes 50,000 participants. Now, what's unique about CLSA or CLSA, or the Canadian Longitudinal Study on Aging, is that it has 2 types of cohorts: the tracking cohort, which comprised of 20,000 people, and these people were followed up via phone, and they had a set of measures that they were asked, while a comprehensive cohort of 30,000 people who were randomly selected and were followed in person and interviewed in person included 30,000 people. And data is available at baseline for both types of cohorts, and it's still ongoing, with data for follow-up 1 being released this year. This study is publicly available, but for a cost, but it's a minimal cost. Usually researchers in Canada pay 3,000 Canadian dollars to have access to the data, and it's free for trainees and postdocs, while researchers from abroad pay 5,000 Canadian dollars to access the data. Now I'm showing you the data access procedure and timeline for the CLSA, but this can also be extrapolated to other somewhat publicly available cohorts studies. It usually takes anywhere between 3 months to 6 months from the time the application to access the data is submitted for the data to be released to you. So for example, for the CLSA, it takes 6 weeks to go through the different steps. Like, there's an initial review by the Data and Sample Access Committee. There's a data access agreement that has to be signed. The data set has to be prepared before you can have access to it. And later on, there's a progress or monitoring report. So the challenges, lastly, in using secondary longitudinal data is that it's prospective research. So the PIs have to live long to follow up the participants. Sometimes outcomes are ill-defined because many mishaps might happen during the data collection procedures, and this is not known to the data users. And data were collected from some other purpose other than what the researchers want to look at. And usually longitudinal studies are now accommodating more aging cohort members, and they have to keep up with the changing times and circumstances, especially with data collection. So some data collection methods such as mailing have become obsolete, as you've seen. So the researchers have to find innovative means of tracking participants and keeping in touch with them. So lastly, I want to share some ways of locating relevant secondary data. So for the US data that I shared on cardiovascular disease, ARIC, WHI, Nurse Health Study, NISA, Cardia, you can find those on BioLink. So NHLBI has this repository of these data sets, and some of them, like the main studies, are open to public use. However, ancillary studies of these data are not for public use. You'd have to contact the main PIs and discuss with them whether you can have access to ancillary studies. There's also databib.org, and there's an open access directory list of repositories and databases for you to check out. Lastly, I hope you've enjoyed this talk, and thank you so much for listening.
Thank you, Dr. Costanian, very much. I hope we will have a few questions from the audience. Also, this is the very first time that we're running such a seminar online. We usually have face-to-face seminars, but I'm happy to see that we have students, we have newly admitted students, we have faculty members, graduates of our program present. So please share your questions.
I thought I saw something in the chat box. Oh, stop sharing.
Yeah.
Okay.
Now, do we have anyone raising hands?
For now, we don't have anyone who has a question.
Okay. No one has any questions?
Any comments? Did you face any challenges while working with longitudinal data that you want to share?
I have one comment for our particularly for our newly admitted students. So don't panic, because many of these ideas are not known to you. We will have, you will go through, epidemiology 1, epidemiology 2, and biostatistical courses. So you will get much more preparation. Okay.
We have one.
Yes, there is one question. Nazeli, go ahead.
Yeah, from Nara Melikan, one of our graduates. Hello, thanks for a great presentation. Would be great to hear about G formula pertaining time-changing variables.
Come again, what formula?
G formula.
Oh, okay. I'm not sure. So this isn't the scope of my talk, and I haven't really used that. So usually time-varying covariates, you have to incorporate them while you are building the model. And the way that you do so is by changing the data from long to wide format, and by making sure that you have this variable across the different time points that it's measured, and that you capture it in your model. So it's not really based on a formula, it's based on how you transform your data to enable the model to include these time varying covariates or variables.
And yeah, Nara continues. Can you share more details about that project and what are the outcome variables? Thank you.
Okay, so I'm currently involved in a longitudinal study, to set up a longitudinal study here in Lebanon to look at the intersection between cardiovascular health and brain health. So cardiovascular health being subclinical markers of cardiovascular disease, such as carotid intima media thickness, heart rate variability, pulse wave velocity, and cognitive impairment. So cognitive impairment has been linked to CVD and to specific subclinical CVD markers. But we're trying to assess as many of these markers as possible in relation to mild cognitive impairment, which is a precursor for dementia and Alzheimer's disease. And cognitive impairment will be measured using various domains, such as executive function, memory, language, speech, and physical function. So those are the main outcomes. Okay. Does anyone have any
other? I have a small question. Are you aware of any longitudinal studies or cohort studies that are looking at COVID-19 patients, cohort of COVID-19 patients?
No, at the moment, no. I'm not aware of, but I know of a longitudinal study that looks at flu, seasonal flu in the US. That's being collected. But for COVID, I'm not sure, although I'm confident that people are going to set up longitudinal studies on COVID soon, sooner or later.
Because here many publications or thoughts is thinking about long-term effects on the brain and its functioning, on other organs, whether it's, you know, for example, the lung damage remains for a longer period of time, or it disappears, and other issues. So it will be really interesting to have a cohort of these patients, of course, after recovery, to follow up for longer term health effects.
Yep. Let's see what happens with this new emerging virus, and its long-term effects are definitely not known yet. So,
okay. Maybe one more question, since we have many students today with us. Would you please share with us as a student, maybe I'm assuming you use this methodology during your doctoral studies, but as a student, like what kind of challenges have you faced in your own research looking at longitudinal data?
One, presence of missing data. It's a real issue, but knowing, like, is it within subject? that's missing, or just for a variable, or how the nature of missing data and how to account and handle it, and also time varying covariates, how to incorporate that. And that's why I stressed on this point, because that's one of the issues that I face, like which variables are considered time varying, and how to assess for their effects in the model, and to make sure that we have all of the correct variables entered in the model. So those are the two challenges. Okay.
Thanks a lot, Dr. Costanian. I would like to read a comment from Dr. Malikian, one of our very prominent faculty members. Excellent presentation. The idea of conducting longitudinal studies about COVID-19 patients would be a good idea for some of our students to start thinking about it.
Sorry, I have to go, Vardi, because I'm not sure about the electricity. Thank you so much for your time.
Thank you.
And I hope it doesn't cut. So now, bye, everyone. Thank you for listening.
Thank you.
Bye-bye. Bye.
Bye. Okay, dear audience, Christy told us that she might have an issue with the electricity in the building, and she had to leave the building. That's why she cut abruptly. Please stay in touch. We are going to organize a series of seminars with other faculty members from different universities. We will be in touch when we have the date and time for our next public health seminar. Thank you everyone for being with us today and for asking interesting questions.
Thank you.
And thank you, Nazali, for organizing everything and having another very smooth and successful event. Thank you. Bye. See you soon.
Bye. Thank you.
Thank you.